Okay, welcome to the Term 1 2022 1B revision session. So we'll just be going through a couple of questions from a past paper. I believe it's semester 2 2018. I think that was actually the past paper that I did when I was studying this course. Not that I remember any of it. So we'll go through a few questions now. I will share my screen. Alrighty, so of course we won't be able to get through the whole paper today, but this was actually the same paper that I did from the Term 3 2021 revision session. The recording is on our YouTube page, so feel free to go look at that past recording, and between that session and today's session, that pretty much covers all the questions in the paper. But we'll start off with question 1A. So this is just looking at some early electrostatics questions. So we've got in the diagram below, particle 1 has a charge of positive 1.0 microcoulombs, and particle 2 has a charge of negative 3.0 microcoulombs. Particles are located on the x-axis and held rigidly fixed. Particle 1 is going to be at our origin, 0, 0, and particle 2 is going to be 10 centimeters from that origin, but still along that x-axis. We have a third free particle with unknown charge q. There is one location where we can put it such that the net electrostatic forces from particles 1 and 2 will be 0, i.e. the third particle will be stationary. All right, so we need to find out where this particle is going to be. So we don't really know what the charge is or where it is, but we'll kind of figure it out. So because we're considering this equation, this problem in one dimension, they're already along the x-axis. We'll put our third particle on the x-axis as well. These two charges are oppositely charged, so it is probably not going to be between 1 and 2. If this is our +1, this is our -3, our kind of field is going to be looking like this. So any particle in here is probably going to move with respect to these two fields. So let's get rid of that. And it will be either on the left or the right. But we're going to assume it is going to be on the left of part I. And that's essentially because it'll be closer to the smaller magnitude of the charge. Because we know our kind of relation between two charges across distances is of course going to be related to the size of the charge and how far away it is from that charge. So we've got one kind of smallish amount of charge and one with a lot bigger charge. And so to balance that out, we're going to assume we've got some particle on this side. And so there's a smaller distance between that particle and the smaller charge, and then a larger distance between this particle with a larger charge. So that kind of balances out pretty nicely. If we were to have a particle over here, it's immediately going to get either attracted or repelled by this large particle, this large charge on this particle, and this other particle is probably not going to affect it all that much. So it's going to be to the left of the two particle system because that is the position where the positive effects over a short distance and a lower charge will balance out the negative effects over a large distance and a large charge. So hopefully you understand the kind of thought process of whereabouts we think it's going to be, so then we can set up our maths and solve for whatever that location is going to be. So we'll use our electrostatic charge equation. So it's essentially our force due to a charge. It's going to be equal to K, that's our constant for charge, just in your data sheet, And it's going to be equal to Q1, Q2 over some distance squared. And we want our charge 3 to be of some distance and charge such that it'll be balancing it out between the force between 3 and 1 and 3 and 2. So let's write that out. So we want K, and we'll put in absolute value brackets because we're not quite sure what that charge of part 3 is going to do. It's going to be Q1, Q3. So this is our Q3, Q1, and Q2. So this is going to be the force between particle 3 and particle 1. And let's call this distance L0. And so we'll divide it by L0 squared. And then that needs to be equal to the force between charge 3 and charge 2. So going to be the same thing, K, Q3, Q2. And this whole distance here is going to be L0 plus L, that distance between particles 1 and 2, which we already know from the question. So that's L plus L0 squared. All right, then we will get rid of terms that are the same. So they've both got K's, we'll get rid of that. And they've both got the charge of Q3, so we'll get rid of that. And immediately we see that it does not matter what the charge on that third particle was. So we didn't get given it in the question, and it's because we don't really need it. No matter what it is, we want to get some sort of position where the effects from the two existing particle charges are going to cancel out. And so it doesn't really matter what the charge on particle 3 was. And so that gives us Q1 over L0 squared. I will still keep that in absolute values, and Q2 over L plus L0 squared. And let's put all our L's on one side. So this is going to be L plus L0 over L naught all squared is equal to Q2 over Q1, absolute values, and that is equal to 3. This was -3 in absolute values, just 3 over 1 is equal to 3. And so rearranging that, we just need to find L0. So I just saw the chat. Yes, so we want the net force to be equal to 0. And so if we just took one of those forces to the other side, essentially we want them to be equal in magnitude, which is why we've put the absolute value sign on the charges. So that'll get rid of any of the signs messing it up. We just want to look at what the magnitude of the forces is going to be. So yes, essentially it's the same thing as the force between 1 and 3 plus the force between 3 and 2 is equal to 0. But because particle 1 and particle 3 have opposite signs, we know one of them is going to be a negative, regardless of what charge sign is on particle 3. And so it's going to be the same as saying the force of particles, the force between particles 1 and 3 is equal to the force between particles 3 and 2. And we're just looking at magnitudes there. Yeah, all good. All right, so then we'll just continue to find out what that L0 is. So we'll say L plus L0 over L0 is equal to square root of 3, square rooting both sides. And our L was already given to us as 10 centimeters. Actually, before we jump to that stage, we can simplify that a little bit. Root 3 L0, taking L0 to the other side. And so what we get is L is equal to L0 root 3 minus 1. If we took that L0 to the other side and took it out front. And so our L0 is equal to L over root 3 minus 1, which is equal to 10 centimeters over root 3 minus 1. So our L0 is about 14 centimeters to 2 significant figures. So that was just the magnitude of L0. So the actual, I guess, location in terms of XY coordinates is going to be -14, 0. So that is question 1A. So not a too bad start to the exam. The tricky part was just figuring out where that charge was meant to be to then go through, solve the maths. And it's essentially just looking at how we want to balance out the ratios between the magnitude of the charges and the magnitude of the distances. And so our equation is, of course, the size of the charges over the size of the distance. So we want small charge over a small distance to kind of balance out a large charge over a large distance, which means it had to be over here. And it couldn't have been between the two charges, even if they had a small distance to the small charge and a large distance to the large charge. That's just because the field caused by those two charges would push the particle along. All right, let's erase that. Well, we already know what F12 is going to be. We want to, and we've already got 1 and 2 kind of in their positions. So it's just about figuring out where particle 3 is going to be. And so we want the distance between particle 3 and the existing particles to balance out, which means we want the force between particle 3 and each of the initial particles to equal to balance out. So that's why we want to consider it in terms of particle 3. Also, when we have the force with particle 3 and particle 1, and then particle 3 and particle 2, we saw that it allowed us to cancel out the charge of particle 3. And because we didn't know what that value was, it had to have been in that form. We couldn't look at the force between 1 and 3 and then the force between 1 and 2, because then we would still be left with a term of the charge on particle 3, and we didn't know what that was. So it was both about the physical system and what we wanted to like equal out, but then also being strategic with the maths to get it into some sort of form where we could cancel out values that we didn't know the magnitude of. Yeah, so that's why we were looking at force 1, 3 is equal to force 2, 3, because we could get rid of those Q3 values. All right, let's move on to question 2. So this is looking a little bit at our Gauss's law and kind of electrical flux. So when a shower is turned on in a closed bathroom, the friction between water droplets and the air can fill the room's air with negative ions and produce an electric field in the air as great as 1,000 newtons per coulomb. That's pretty wild. So we're going to consider a bathroom with dimensions 2.5 meters times 3 meters times 2 meters along the ceiling, floor, and 4 walls. Approximate the electric field in the air as being directed perpendicular to those surfaces at those surfaces as having a uniform magnitude of 600 newtons per coulomb. Also treat those surfaces as forming a closed Gaussian surface around the room's air. What are the net flux? Be sure to include the sign and comment briefly on why the net flux has the sign it does. All right, so Gauss's law, the closed integral of the electric field times the area of our Gaussian surface is equal to our kind of flux value. And we were told to use our room as the full Gaussian surface. So let's figure out what that area is. So surface area of the room is going to be 2 times 2.5 times 3 plus 2 times 3 times 2 plus 2 times 2 times 2.5. So that's for each of the walls of the room. We've got like 2, 2.5, 3, just area, surface area of a rectangular prism. So our total surface area of our room is going to be 37 meters squared. We were told that the electric field for going through each of these surfaces of our Gaussian surface will approximate as being directed perpendicular and having a uniform magnitude of 600. So our E dot dA and closed integral is just our electric field through our Gaussian surface. We are told that this is 600 and our area of our Gaussian surface is just our area of our room. It's 37 meters squared. And we said that it's going to be perpendicular, so we don't have to worry too much about this dot product affecting it. It's just going to be straight as it is. So it's 600 times 37. And that is equal to our flux. So our net flux for the room is equal to, there is a negative in there somewhere, I believe. But what we end up with is 22 times 10 to the 3 in our units. Oops, per coulomb. There we go. All right. Our negative sign is there because we are working with negative ions. There we are. So that's our answer for part I. Part 2. Find out what the enclosed charge is. So still using our Gaussian law, our net flux is equal to the enclosed charge over the permittivity of free space. And essentially, we're just going to use what we previously found. So our enclosed charge is equal to our net flux times that permittivity. That is 22 times 10 to the 3. And our permittivity is 8.85 times 10 to the negative 12. Put that in our calculator and we get negative 1.9 times 10 to the negative 7 coulombs. It is negative because they are negative charges. So even if you're like not quite sure what the sign should be in the general form of the equations or how it's considered when we're solving it or given in the question, we know that these charges we're working with are negative ions. So regardless of what happened in our working out, at the end, our enclosed charge should be negative. And our flux should also be negative because it's a flux of charges going through this kind of surface. Part 3, the volume charge density rho. So our charge density is going to be rho is equal to the enclosed charge over the volume of the room. Our volume of the room is just timesing each of the dimensions of that rectangular room. That is 2.5 times 3 times 2. We have our volume of the room as 15 meters cubed. So our charge density is going to be our total charge, negative 1.9 times 10 to the negative 7 over 15 is equal to negative 1.26 times 10 to the negative 8 coulombs per meter cubed. And finally, part 4, the number of excess elementary charges, E per cubic meter of the room's air. So part 4, essentially we're saying how many charges could make up this charge density if they were all electrons. So the number of electrons is equal to the charge density divided by the charge of an elementary particle. And it's essentially saying negative 1.26 times 10 to the negative 8 over negative 1.6 times 10 to the negative 19 is equal to 7.8 times 10 to the 10 electrons, yes, per unit volume. So that's the end of that question. Essentially, we were given an electric field as a result of all these charges within inside a rectangular room. We used our Gaussian surface, our Gaussian law, to define the whole room as our Gaussian surface. Luckily, the electric field could be assumed as perpendicular to all those surfaces. So that simplified this Gauss's law equation to just the electric field magnitude times the area, which was 600 times 37. We found our net flux, noting that it was negative because we had negative charges. Then the enclosed charge, just timesing that net flux by the permittivity, again, making sure it was negative because we knew they were negative charges. Then we found our volume charge density. So that's the total enclosed charge divided by the volume. So what we get is our charge per unit volume. And then we divided it by the charge of an elementary particle to find out how many particles were in per unit of this volume in this very charged shower room, which is a little bit of an interesting situation to build a maths problem along. All right, so let me know if there are any questions about that one. Otherwise, we will move on to a little bit of magnetism. So question 3. In the figure below, an electron accelerated from rest through potential difference V1 is equal to 1 kilovolt enters the gap between two parallel plates having a separation of D is equal to 20 millimeters, and potential difference of V is equal to 100 volts. The lower plate is at the lower potential, and neglect fringing fields and assume that the electron's velocity vector is perpendicular to the electric field vector between the plates. In unit vector notation, what uniform magnetic field allows the electron to travel in a horizontal line in the gap? That is a lot of words, so let's digest what is going on in this question. So we've got a moving electron. This is our electron from rest through a potential difference of 1 kilovolt. The potential difference between these two plates is V2, and we're probably going to have our electric field just along here. We're going to ignore any like bulging effects around the side. We're going to assume it's perfectly straight down. And we've got the lower potential on the lower plate. So I believe we should be going from higher potential to a lower potential. That makes sense. An electric field, and then we want to figure out what kind of magnetic field we can put through this system as well to make sure that our electron isn't going to be influenced by that electric field. So we know that this electric field and magnetic field forces, when they're influenced by a moving charged particle, they're going to be perpendicular to each other. And we also know that our forces as a result of each of these fields are going to be just by the equation. So the force due to the electric field is going to be the charge times the electric field. So it's going to move in that same direction as the field. And then force from the magnetic field is going to be QV cross B. So that's our velocity of the electron and our magnetic field, our B field. And so we want them to be equal. So we're going to have QE is equal to QV cross B. And we can get rid of the charges. So what we're working with is we want our electric field to equal to the velocity times the B field. And first of all, we need to get our velocity. So essentially, we can get our velocity from a kinetic energy equation. So our kinetic energy is equal to half mv squared. That's our kinetic energy of the electron. And it is going to be equal to whatever made it have that kinetic energy. And that is when it was accelerated from rest through the potential difference phi1. So at this point, it was at rest, but once we added this phi1, it sped it up, it gave it its kinetic energy. And so that is equal to the electron charge times the potential of 1. So potential is kind of, same sort of wording as when we were looking at potential energy with like gravity or springs in 1A. And so it kind of works the same way. Because of this added potential, even though it's in like volts, which is a little bit interesting for a potential, it does correspond directly to the gain in kinetic energy, just looking at classical mechanics of the whole thing. Rearranging that, the velocity is equal to the square root of 2 times EV 1 over m, equating those two values and rearranging for velocity. And we can put in those values. That's 2 times 1.6 times 10 to the negative 19, and timesing it by 1,000, which was our 1 kilovolt. So 1 kilovolt is 1,000 volts. Over our mass of an electron is 9.1 times 10 to the negative 31, just from your data sheets. And solve that in your calculator and you get a velocity of, I believe that's 1.8 times 10 to the 7 meters per second. And we've pretty much got enough to solve for our magnitude of the B field. So we want our B, our magnetic field, to equal to the magnitude of the electric field over the velocity. So first of all, we're just looking at magnitudes before we then start thinking about the direction. So our electric field was V2 over D. So just as an aside, the magnitude of the electric field is equal to the potential over the distance between the two plates. So we can put that in. That was V2 over D, and then times our velocity. Of course, our velocity kind of looks the same as V, so we'll put a little curl on it so we know that that's our velocity. Our separation was 20 millimeters and our potential 2 was 100 volts. So we'll put that in. That is 100 volts over 20 times 10 to the negative 3, timesing it by our velocity, which was 1.8 times 10 to the 7. And we solve for our B field, and that is 2.7 times 10 to the negative 4 Teslas. And then, of course, if we're talking about fields, we must talk about directions. So we've got our electric field going downwards. We must find some sort of B field that stops our electron going downwards as well. It must be in some direction which causes our electron to go upwards to oppose that. So we'll just use our right-hand rule. Basically, the way that works is we take our pointer finger as the first vector in our equation. So in this case, our pointer finger is going to be velocity. So velocity, our B field is then our middle finger, and it goes perpendicular to that. This is the way I do it. Sometimes it might be like whichever way your palm goes, but I like to do this method with the 3 fingers. So pointer finger of velocity, the middle finger, which kind of is like flipping somebody off in your class, is going to be the next vector in the equation. So this is going to be the B field. And then your thumb points out perpendicular to those 2 fingers as the resultant vector. So we want the force to push it upwards, and we know it's going in that direction. And so what we get is our third finger, which was our B field, or the second vector in the equation, must be pointing into the page. So, and it's going to be a little bit stupid to do this right-hand rule when you're doing an exam, but it'll save you so often. Make sure you are using your right hand, but essentially that gets us B field is into the page. Blah, blah, blah. So our final B field is 2.7 times 10 to the negative 4 Teslas into the page. Okay. that is question 3. So let me know if you have any questions about that, but otherwise we are about at the halfway point, so we'll move on to some of the later topics of this course, which is looking at our kind of optics and introductions to quantum mechanics. So question 5a, we are looking at Young's two-slit experiment. We've got two wavelengths. Lambda1 is equal to 750 nanometers and lambda2 is equal to 900 nanometers. So illuminate a pair of slits spaced by 2.0 times 10 to the negative 3 meters, and they will produce an interference pattern on the screen, about 2 meters from the slits. Find the minimum non-zero distance measured from the common central point of the fringe position, at which a bright fringe from one interference pattern will coincide with a bright fringe of another. So basically we've got these two slits and we've got two light sources. Let's say green is our lambda1 and blue is our lambda2. I don't think that physically corresponds to it, but basically they'll come through like this and they'll both form a bright spot in the middle and then some other interference patterns alongside. These are other bright spots. So they'll coincide with the same one in the middle, but then it's going to be a little bit different coming outwards. So I think if it's got a smaller wavelength, then we'll probably have closer together slits. And so we just want to find out when, after the middle one, when the next two bright spots from each of them are going to correspond to each other. And let's just find that out in the maths. So this is 2 meters difference. And this slit is 2.0 times 10 to the negative 3 meters. All right, so what is our equation for this? The distance ym is equal to the index of whatever maximum we're talking about. So this is the distance from the center of whatever index m we're looking at. So m could be equal to 0, 1, 2, blah, blah, blah. So m times d, our distance between the viewing and the slits, lambda over d, the distance of the two slits. And essentially we want a bright fringe from each location. So let's take a ratio of that. So let's say we want ym is equal to m d lambda1 over d for lambda1, and then we'll say yk for the index of the second one is going to be equal to k d lambda2 over d. And we'll take a ratio of that. So the ratio between the indices of m and k, m over k, is going to be equal to the ratio of the wavelengths, which is lambda2 over lambda1. They're going to be at the same point because they're both on the same denominator. I guess a more direct way of saying it is when these two things are equal, we're going to have m d lambda1 on d is equal to k d lambda2 on d. Get rid of those, and put k on that side. M over k is equal to lambda2, put lambda1 on that side. So essentially equating two of those maximums for when they're going to correspond. We don't know what the indices are going to be, but we do know what the wavelengths are going to be. And just looking at the ratio between them, this is going to be 900 on 750, and to correspond that to two integers, that is about 6 on 5. So those are the two lowest integers we can use to create that ratio between the wavelengths. So we can pretty much assume that m is equal to 6 and k is equal to 5 are going to give us the indices of two maxima points that are going to overlap with each other. So Y6 for, I guess, the lower frequency is going to be equal to 6 times the distance between the slits and the viewing point, which was 2 meters, times the wavelength, which is 750 times 10 to the negative 9, converting that nanometers into meters, dividing it by the distance between the two slits, which was 2 millimeters, or 2 times 10 to the negative 3 meters. And that gives us 4.5 times 10 to the negative 3 meters. And that is about 4.5 millimeters. So at 4.5 millimeters, the fifth maxima of the blue, or the larger wavelength, is going to correspond to the sixth maxima of the green. So let's redraw that. So that's for 1, 2, 3, 4, 5. And then for green, it's going to be about like 1, 2, 3, 4, 5, and 6. So at 6 for the green and at 5 for the blue, they'll overlap again, and that'll occur at about 4.5 millimeters from the initial maxima. All right, so that one wasn't too bad, just using the equations, subbing in the numbers that were given, and just figuring out what the two lowest integers could be for our indexing of those maxima points, which we found out by just rearranging the equations and looking at the ratio between the wavelengths. And so that was able to give us that value. Of course, there might be another overlap for higher wavelengths, but we wanted to find the first instance where they overlapped after, of course, the initial center point. All right, and this is the last question that I have prepared for this revision session. It is going through a little bit of Heisenberg's uncertainty principle. So consider the implication of the Heisenberg uncertainty principle for the probability of locating fundamental particles within the atom. The diameter of a typical atomic nucleus is 5 times 10 to the negative 15 meters. If we take the position of uncertainty for a proton to be the nuclear diameter, calculate the smallest uncertainty in momentum and the energy in electron volts of the proton. All right, so part I, we've got a nucleus diameter. So let's go, diameter nucleus is equal to 5.0 times 10 to the negative 15 meters. And our Heisenberg uncertainty principle is the uncertainty in x times the uncertainty in momentum is greater than or equal to our h bar over 2. That's all weird notation. There we go. It's a little bit better. So we're saying that in a particle, our proton is going to be somewhere in the nucleus. We can't pinpoint exactly where it is, but we know it's going to be somewhere between that region. So we can put that in as our uncertainty in x. Then we can make this equation as the, we can make uncertainty in momentum the first value here. It's going to be greater than or equal to h bar over 2 times the uncertainty in x. And we'll just put in the values for that. So the uncertainty in momentum in x is going to be greater than or equal to our h bar. It's 6.63 times 10 to the negative 34 over 2 times 2 pi, because this is just for h bar is equal to h over 2 pi. And then timesing it by 5.0 times 10 to the negative 15. Put that in our calculator. That is 1.055 times 10 to the negative 22 kilogram. I think that's meters per second. Can't read my handwriting anymore. whatever the units are meant to be. All right, yeah, that makes sense. Our momentum is just mass times velocity, so kilograms meters per second. Okay, so if we take the position uncertainty for proton to be the nuclear diameter, calculate the smallest uncertainty and momentum and the energy. So that's our momentum. And essentially we can get the energy out of our energy equations. But first, we need to figure out if we can use our non-relativistic energy or if we have to account for relativity. And to do that, we're going to see what the velocity is. So our momentum is equal to mass times velocity. And we can essentially say our velocity kind of range we're expecting is going to be the uncertainty or the range in momentum, dividing it by the mass. So that is 1.055 times 10 to the negative 22 over 1.67 times 10 to the negative 27 for a proton. And that is about 6 times 10 to the 6 meters per second. Our speed of light is approximately 3 times 10 to the 8 meters per second. And so we're still quite a bit smaller than that. So if it was to the order of 10 to the 8 or 10 to the 7, we might be a bit concerned, but 10 to the 6 is quite a bit smaller. So we're going to use non-relativistic energy. Relativistic. So it is important that we made that check because that simplifies our equation a bit. And so what we're going to use is E is equal to P squared over 2M. And so our uncertainty range in energy is going to be equal to our uncertainty range in momentum squared divided by 2M. And that is just 1.055 times 10 to the negative 22 in brackets squared over 2 times the mass of the proton, 1.67 times 10 to the negative 27. And that gives us 6.6 times 10 to the 14 joule, no, sorry, to the negative 14 joules. Then to convert that into electron volts, we need to divide it by the charge of an electron, and that gives us 412 kilo electron volts. Again, if you forget the conversion between joules and electron volts, it's an online exam, you can just Google it, just to give you a sanity check for that one. But that is our energy range for a proton in a neutron and a nucleus, sorry. All right, so repeat this calculation for the electron. All right, so essentially going through the same path, what we get is our energy is approximately like several mega electron volts, using the same kind of uncertainty in displacement. And it is so much bigger because the mass of an electron is approximately 2,000 times less than the mass of a proton. So as a result of that, we get a huge energy. I won't go through it, but it's essentially the exact same steps, just subbing in the numbers for an electron. And then hence provide comment on the probability of finding these particles within the nucleus. All right, so our uncertainty principle, our uncertainty in X times the uncertainty in momentum greater than or equal to h bar on 2. Essentially, we're looking at the size of the energy and seeing if that's kind of feasible. So we've got a relatively small energy for the energy range of the proton in a nucleus. That's about an acceptable range. So it's pretty reasonable that our proton is going to be somewhere within the nucleus. However, when we looked at an electron, you get out an energy that is to the scale of mega electron volts, and it gets quite a bit larger. So comparing the two, it seems significantly less likely that the electron is going to be within the nucleus. So essentially, we're saying proton is likely to be found in that uncertainty in X, so be found in the nucleus. But for the electron, energy is unphysically high. Therefore, unlikely to be found in the nucleus. Of course, we know that just by looking at kind of like charges and whatnot and how that works on an atomic level, but just by looking at the uncertainty principle with those small sizes and then considering the, I guess, mass of an electron and that uncertainty principle, we get an energy that's too large to make sense. So we're going to say that our electron, the uncertainty in distance for our electron is probably going to have to be a larger range, and that corresponds to the outer shells of an atom rather than being in the nucleus. All right, so we do have a bit of time. So just to fill it up, I might just quickly go through one of those other quantum questions. So this was something that I did in the previous year's revision session. So it does exist as a recording. So if you happen to be watching this in the future and you're watching this recording as well as last term's recording, you can stop here, give yourself a little bit of a break. But just to complete this revision session, this is question 6A. All these questions were from the T2 2019 paper. Oh no, sorry, it was the semester 2 2018 paper. So this was a square potential well with infinite walls of a solution, for a square potential well with infinite walls, the solution are of the form of this phi of x is equal to a sine knx. So our phi here is our waveform of some sort of particle or level within the potential well, and it is a sinusoid for each index of n is equal to 1, 2, and 3. So to start out with this question, they're essentially asking the meanings of the symbol in this expression. And basically we draw it out like this. So we've got this infinite potential, and then between the distance of L of our potential well, we're going to have some sort of energy level, and it looks like a sine wave. On either side of our infinite potential well, we've got some sort of infinite, I guess, amount of potential such that it's a physical wall in which our particle or anything in our potential well can't get through. So our wave equation during these regions must be equal to 0, but it will have something when it's inside the well. And that's where there's no potential to, I guess, stop our particle. So our phi, our psi, that's what our curly trident looking thing is the wave function. It contains information about the physical quantities of a system. And so we can use this to find the statistical probability of finding a particle at any location within that well. A is our normalization constant. That's just a bit of maths to help it all fall out nicely. And Kn is the wave number of the nth state, so the nth energy level. Question 2. Show that the expression is a solution of the time-independent Schrodinger equation. So we'll just get out our time-independent Schrodinger equation, which is of this form here. That's straight out of your formula sheet, or you can Google it if you forget, or flip through your notes. It is, of course, our open book online exam. And for an infinite potential well, we are just considering the region within inside those infinite walls where the potential is equal to 0. So this term with a potential u can just go to 0. Our psi, our wave equation, will take the second derivative with respect to x. Easy peasy, just deriving sines and coses. We take the wave number at the front, then from cos to sine, we get our negative as well. And so we just put that straight into our time-independent Schrodinger equation. Then we can cancel out some of the values. And essentially we see that it does fit well, and our energy will be equal to h bar squared over 2m times kn squared. So it's essentially saying, can we put this equation into our time-independent Schrodinger equation, where we'll get some sort of form where it equals out. And we also get out a form for our energy. If there was like some extra terms here, blah, 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 then it might not fit. Maybe there's something else that we didn't consider. But it does fit nicely. It is equal to the waveform times 2 of these constants. All right, question 3, rewrite this solution in an expression including the width of the well L. So we want this solution equation to be in the form of something where we also consider the size of L. So essentially we are looking at changing the wave number. Our form of the wave equation is just our normalization constant times the sine of the wave number times the x. We don't really change our normalization constant. That's just slapping it on the front to make the maths all nice. So it's really our wave number that we're changing. And the way we can do this is by subbing in values that we already know. And that's at the boundary conditions, our wave function is 0. So due to continuity, our wave equation must be a continuous smooth line, which means in the walls, our wave function goes to 0 because we've got that infinite potential there. But our wave inside the well, it must go back down towards 0 at these boundaries so it can continue out as 0. And that is existing at x equals to 0 and x equal to L, the boundary of our equations. And so we'll just put that in. So psi of L, we get a sine KL is equal to 0. And essentially we can figure out at what point the values in our sine equation, we will get a 0. We probably can't use it for psi of 0 because if we just put 0 in there, then it all goes to 0. It doesn't make much sense. We already know sine of 0 is equal to 0. So we'll use sine of L. Sine of KNL to get our values. So for a sine wave, we know if we've got some integer multiple of pi, we will get a 0 there. So just drawing our sine wave just as a sanity check. For every integer multiple of pi, we will get 0. So in order to get our sine of the wave number times L is equal to 0, it's going to be equal to K and L is going to be equal to some integer multiple of pi. And so we can rearrange that for our wave number. Kn is going to be equal to n times pi over L, for n is equal to any integer. And that corresponds to any integer of our wave number function. And at this point, it becomes really clear as to why we've got discrete energy levels in our potential well. It's not just going to be some random number or continuous function. It must be discrete because of that continuity. And so we can write our wave equation as equal to a sine n pi x on L. So now we've got our solution to our infinite potential well in terms of the width of the well L. And then part 4. Using part 3, find the expression for the probability density Pnx and sketch and label that probability for the first 3 combined states of the well. So just quickly finishing that up. Our probability function is going to be equal to the integral across the distance x and it'll be this psi star times psi, which is the complex conjugate of psi. Because our equation for our wave function is already real, that just corresponds to psi squared. So we can put in our equation for psi, we can square it, put it into that function, and that's essentially our probability density. We won't solve it there, that's the general form. And then to draw it, it's just going to be, for our first one, it's just going to be that one bump. Our second one, going to be the 2 and third, and so on. So that's just the general drawing of that. Probability, basically square of wave function. So that's the physical meaning that we get out of our solution to those potential wells. So that is the end of this revision session. I hope you have found this helpful. Thank you for joining me, and we will see you next time. Good luck for your exams.